Just as a reminder that I'll have office hours today from 3 to 5. If someone needs to show up, you can also email me after that. You still have 20 minutes to upload the answers. Yes, after you finish the exam on my lab. Another thing, I don't know if you have. It's for like to non-upload to upload. It's just like the practice exams. Like in terms of like how it's structured. Like I don't know if you realize, but it could be useful to know is that like on the non-upload programs, like each box um, is graded independent of one another of every other box on that problem, but each one is worth the same number of points, right? So if it's like 8-point problem and it has 4 boxes, it means like each box is worth points. I don't know if you need head figure, but it can not word problems. That's actually more related to what we're going to do today, which is more into Lagrange multipliers. So yeah, we don't really have like word problems like the real actual word problems that make sense in this course require Lagrange multipliers, which is precisely what we're talking about. But yeah, the optimization problems are like, I think if you look at the practice exams, they're just like, here's like a function and whatever. But yeah, for the useful, in fact, I was going to start with the word problem. So let me share this on the iPad. Here's a interest. So yes, I was saying we're going to talk about Lagrange multipliers. So here's an interesting problem, or more somewhat useful problem. So let's say that you want to build a box, right? With no top, so it's like an open box. So so that two things happen. The surface area of the box is well, I don't know how much is a realistic surface area. Maybe let's say 10 feet square, but I don't know if that's actually too much or too little. But I'm just like, you'll see. I mean, this is just to make it more realistic, but just to give a number. And the volume of the box is as big as possible. So if you try to draw a box, let me see if this comes nicely. So yeah, Amazon has hired you to design their boxes. Well, I guess this would not be like a useful box because it's open. So it's more like a moving box, right? Where like you just put things on the box, but you don't care if you have to seal it, right? So here's your box, right? Um, let's call well a box like let's say maybe it has a side here that we call X. Let's call this side X. Let's call this side Y. And let's call the height Z, right? That those names make sense. So what's the volume of the box? In terms of X, Y, and Z. X, Y, Z. Good. And what's the area of the box? So again, like the useful thing is like the area is like that's sort of like the amount of material that you actually use to build the box. So it is just like the sum of the areas of each side of the box, right? Exactly. So the area of the box is xy plus 2xz plus 2yz. You see like it's only xy because there's no top, so xy is like it's just like the area of the bottom, and then the like front and back and these two other sides they come in pairs, so that's why you have like a 2 in front of the other two quantities. Is that making sense? So again, like this is sort of like the amount of material that you're going to use to produce a box. And the conditions of the problem is that we want this quantity to always be 10, right? Because of this condition that was given to us. So like, again, like if you are like a company, your objective is usually to maximize your profits. Oh, no, not much has happened. I'm just saying like we're doing like an optimization problem where you're building a box, but the conditions for building the box is that the surface area of the box is set to 10 feet squared. Okay. And so like we just found the area of the box, and so that should be 10. And what I was saying is that, right, like if you think of 10 feet square as the material that you have to build the box, you could imagine using different designs, and among all those designs whose area is 10, you want to choose the one that gives you the biggest volume, because that's where you would be able to put the most amount of stuff, right? So that makes sense from like optimization capitalistic perspective, right? Now, the point is that there are actually two ways to solve this problem, okay? So there are two ways to solve this problem. Option one is to turn, so really the goal is to maximize the volume, right? So that's the goal. So the goal is to maximize the volume. Okay. Now, if you think of what we have done thus far, like the criteria, like we have been finding critical points or like max and min of functions of two variables, right? So the first thing you could try to do is to turn the volume into a function of two variables so that you can apply the tools that we have used up to this point. So here's the strategy number one. Turn the volume into a function of two variables. So that you can apply what we did before. In order to apply the methods from before, now how can you turn the like the volume a priori looks like a function of three variables, right? How can you turn it into a function of two variables? Yeah, you can use the second equation, right, to solve for z, right? So here's like how we would do this. So you have this equation. By the way, this equation typically in this context will be called like the constraint equation because it's constraining the variables x, y, and z. So this will soon be called the constraint equation. Okay. And so how can you solve for z? You can say that 2 like z times x plus y equals 10 minus xy, right? So I just like subtract xy from both sides, and then I factorize 2z in the last two terms. Is that okay with everyone? And so this is like how you could write z as a function of x and y from this equation. So far, so good. And once you know z in terms of x and y, you can plug that back into the volume formula. So the volume, which was originally xyz, becomes xy times 10 minus xy over 2 times x plus y. So it becomes 10xy minus x squared y squared over 2 divided by x plus y. Or if you want 2x plus 2y. Is that okay so far, so good?
One quick question. Could you please explain why there are constraints again?
Sorry, what about the constraint?
Why are they there again? Could you please explain that part?
Oh, it's just that I'm saying, like, if you just want to build a box, right? And there, if you just, if I tell you, okay, I want to build a box of whose volume is as large as possible, right? If you don't give me any restrictions, right? Like you could just keep making the box bigger and bigger. You could make the box of the size of the Earth, and then the size of the solar system, and and then the size of the galaxy, and then whatever. The only way for this problem to become interesting is that if you have some some extra condition that tells you, okay, yeah, but your box must satisfy at least some other property, right? Is that making sense? Because otherwise the volume could just grow as much as you want, right? And so, like, what you could be asked to do is like, okay, you do want to build a box which is the one that has the largest volume, but the condition is that the area has to have this particular number, this particular size, because otherwise, again, like there would not be any control whatsoever on the function, on the volume, right? So that's why this is called a constraint, because it's like preventing you from just go crazy and just doing like starting taking larger and larger values. Is that better now? And so now that we have a function of two variables, what should we do? So now we're thinking of the volume as a function of two variables, right? Let me call it this function like f. So now that you have a function of two variables, how do you determine if there's like a max or a min? Good, take the partials and let's try to find the critical points. Yeah, so what's the partial derivative with respect to x? And this is interesting because it's like a quotient rule, right? If you remember, the quotient rule is you take the derivative of the numerator. So the derivative of the numerator with respect to x is 10y minus 2xy squared times the denominator minus the numerator times the derivative of the denominator. The derivative of the denominator is 2, right? So it's just minus 2 10x minus x squared y squared. And this is divided by the denominator squared. Does this look familiar? So this is like the usual quotient rule, right? Is that okay? Is that making sense? Let's see. Oh, right. Yes, this is kind of, I agree, this is kind of annoying. And what can we simplify here? Well, these two go away. And then you can factorize a y squared, right? Everything has a y squared. So, oh, and these two, I mean, they don't cancel, but they can be combined. So you get 20 y squared minus 2x squared y squared minus 4x y cubed over 4x plus y squared. And so you get, you get y squared times 20 minus 2x squared minus 4xy over 4x plus y squared. Well, actually, like the whole point of this example is that you don't want to do this. This is why we're going to do a second method, but it's sort of like you feel the pain so that you know that this is not what we're going to do in general. So you get y squared over 10 minus x squared minus 2xy and over 2 over x plus y squared. I mean, well, a function like this could be on, I mean, a more friendly function, it could be on the exam, but like the whole point of a problem, like a word problem like this is more like a Lagrange multiplier problem. So strictly speaking, like if it's given in this context, like it's not really on today's exam. Like what I'm doing right now, it is like, you know, like finding the critical points and setting them equal to 0. That is on today's exam, but not not when the function comes like from such a, from this perspective. So yeah, like if I give you like a function, you should be able to find the partial derivatives and set them equal to 0. But like the point is, like in this for these kinds of problems, this is not what you're supposed to do. Like I'm just trying to do it this way so that you see why you're not supposed to do that, right? You see what I'm saying? Because like as someone pointed out, like this function has like partial derivatives which are very complicated. So like the whole point is not to do it this way, but I'm showing you how you would get it done. Good. So this is one of the partial derivatives. And then if you just do what you're supposed to do, well, not what you're supposed to do, but what I did, which is go to Wolfram alpha, you can also find the other partial derivative with respect to y. So then, and then we Wolfram alpha. You find that the partial derivative with respect to y, I mean, you do it the same way, you know, it's not that different. Like at least I wanted to do one of the two, like by hand so that you would compare like how it should be. It's essentially the same. You get x squared times 10 minus y squared minus 2xy divided by 2 over x plus y squared. No, Wolfram Alpha is not the second method. But it could make the first method like a lot friendlier. But no. You'll see. Okay, but so we find the two partial derivatives, right? And now we set them equal to 0. So we need the partial of f with respect to x to be 0, the partial of f with respect to y to be 0. And so that means that you want y squared over 10 minus x squared minus 2xy divided over 2x plus y squared to be 0, and x squared times 10 minus y squared minus 2xy divided over 2x plus y squared to be 0. So far, so good. Are there questions about this? Now, how do you solve this system of equations? What's the first thing you can say if you want to solve this system?
X and y can equal 1 or -1, or sorry, 0.
Well, that's one thing. That's one thing you can say, but there's something even more immediate. Well, maybe not immediate, but yeah. How can a fraction be 0? What do you need if a fraction is 0? This is like a ratio, right? What's the only way for a ratio of two numbers to be 0? The numerator, yeah. The
numerator.
Yeah, so you can just completely forget about the denominator in these two equations. So you need the numerators to be 0. And at least now this looks a lot less intimidating. Is that making sense? And then you say, okay, let's look at equation 1, for example. So let's start with equation 1. Equation 1 says that y squared times 10 minus x squared minus 2xy should be 0, right? And here is again, like, when can the product of two numbers be 0, right? The product of two numbers is 0 when at least one of the numbers is 0, right? Is that okay with everyone? Is that making sense? But what would the volume of the box be in the first case? What would the volume be in this case? It would be 0, right? So this is not like an interesting box. So you can just forget about it because you're trying to make the biggest box possible. So it's definitely not going to be 0, right? Is that okay with everyone? Like this is a good thing about the fact that this is coming from like an applied problem, that there are cases that you don't really have to consider anymore because you're trying to make the biggest possible box in terms of volume, and that's not going to be the one that has volume 0. Is that okay? So that means that the only equation that you have to worry about is the second one. And again, like for example, you can use this one if you want to say that y, like, then that means that 10 minus x squared equals 2xy. And so 10 minus x squared over 2x equals y. Is that making sense? In fact, let me just write it. I'll keep it this way because you'll see in a second that it's more useful to write it this way. Let's go to equation 2. What does equation 2 say? So again, you have two possibilities. You have a possibility where x equals 0, right? Or 10 minus y squared minus 2xy equals 0. Right, but what happens if x equals 0? It's the same situation, right? Like the volume would be 0. And so this is not interesting. And so the only possibilities were 10 minus y squared minus 2xy equals 0, which is the same as saying that 10 minus y squared equals 2xy. Is that okay? So far, so good. I don't know if you see what's about to happen, like if you compare the two equations that I have put on boxes. What can you say now from both equations? Right, like good. You see, like you have on the right hand side 2xy, right? So you can say that 10 minus x squared equals 10 minus y squared. And that's the same as saying that 0 equals x squared minus y squared. So 0 equals x minus y or x plus y, right? But again, like a box like x, y, and 0 are like all positive numbers because those are the sizes of a box. So only x equals y is an interesting case.
Wait, doesn't that make our denominator 0? No, was it x minus y or x plus y?
Well, x minus y is not allowed for a couple of reasons. Yeah, that would make the denominator undefined, if that's what you're saying. Is that what
Yes.
you're? That's one option, one reasoning. But another reason is that you want x, y, and z to be the size of a box, so they should be taken to be positive, right? And this one is saying that they have opposite signs, right?
Yes. Okay.
So you can, I mean, you can discard it either because the derivative becomes undefined or just because it does not make physical sense. So this one is not good since all sides should be positive quantities. Are the size of a box, are the lengths of a box, are the lengths of the sizes of a box, right? So we have that x equals y, right? So now we know, thankfully, that x equals y. And then you go back into your favorite equation that we had used. Like, for example, you can substitute that into like the equation that I wrote before, like 10 minus x squared equals 2xy. And so now this becomes 10 minus x squared equals 2x squared. So 10 equals 3x squared. And again, because you only want oh, I don't know the meaning of so many backslashes, but now you can say that x equals 10 over root of 3. Okay. No, it's okay. And then y equals x, so y should be 10 over root of 3. Okay. And then what was supposed to be z? Z could be found from the constraint, right? So just to go back for a second, z. Oh, yeah, good. Excellent. I agree. Thanks. Perfect. And just to go back for a second, z was long time ago 10 minus xy over 2x plus y. Well, and that is whatever it is, because MyLab at least would recognize that as an answer. So you don't need to simplify it, and I won't either. But so we found the sizes of the box, right? And so in fact, if you want, let me show it to you. So those are the sizes that you would need to use for the box. And if you go to GeoGebra, right, again, like you can check with the second derivative test that these values for x and y do yield a max, but we will cheat and just look at the graph. Can everyone see like this orange graph? So that's the graph of this function, like xy minus, like that's the graph of the function of the volume function, basically, in terms of x and y. And you see here is like the point the square root of 10 over. I mean, I don't know if you see the point A, like if you see this point A, those are the values of x and y that we found. And you see that like it sits like on what seems to be right up below the peak of the graph here. Is that clear?
Yes.
And so you see it does seem to yield the max. So like, let me make it bigger. So yeah, above this point A should be the max, like should be the top of the mountain. So this is why x, y do yield the maximum. Okay. But like the point of all these strategies that it's like a tedious thing to do. Okay, it's not very friendly. So I'm going to teach you the friendly way to do this. So let me go back to the iPad. So so this again, this is what we were doing, and now let me tell you the option number 2, which is called the Lagrange multiplier method. The whole point of, in a nutshell, the point of Lagrange multipliers is that you work with the 3 variables at the same time. So you don't try to kill one of the variables. Like all of this happened because you wanted to turn the function, like, you know, everything was in principle like a function of 3 variables, but you insisted on turning it into a function of 2 variables. So all this mess happened because you tried to do that. Okay, so the method of Lagrange multiplier is that you work with all the variables at the same time. Without trying to eliminate one of them. Okay. So what's the idea here? Again, like the function, now think of this as a function of three variables. The volume. You have this function of three variables. Okay. And then you have this equation, which I call the constraint, right? Now, this is actually something that you should know for today. What does, like, if you look at this equation, what does this type of thing reminds you of? When you say like
Partial derivatives.
well, it is more like it's similar to the equation of a plane. Okay, you have like a bunch of an expression of three variables being set equal to a constant, right? So what happens when we set something equal to a constant? What was the name for that?
Surface?
It was, this is like a level surface, right? For like, this is like the level surface of g of x comma x, g of x comma y comma z equals xy plus 2xz plus 2yz, right? Like if I had like, well, the tangent plane is about to appear, right? But if I had like if I have like, you know, like an expression involving x, y, and z in being set equal to a number, that is like essentially like another name for a level surface. Is that making sense? So let's see if I can make it here. In fact, if you want me to show it to you, that's like the level surface for this function. Like that's what you get if you said like, that's what you get if you, that's how the equation, like the level surface looks in this case. So on all these points, like xy plus 2xz plus 2yz equals 10. Okay. So
would 10 represent the value of z at that level surface?
yes, this would be like what we're called, like in what we called in the problems like little z, right?
Yeah.
Yeah. Good. So what I'm trying to say is that if you can think of this as like some, oh, it was like a complicated creature, but like, you know, you have like your, you have like some sort of thing here. And this is like what we are looking at. Now, someone mentioned on the chat tangent planes, which is a good thing to have said, because so the points on this surface have tangent planes, right? And what was the normal vector to these tangent planes?
The gradient of the purple function at that point.
Correct. So the tangent planes have normal vector equal to the gradient of the function. Yes. Right. Is that making sense? So, and then, okay. So you have this surface, you have these gradient vectors, which are perpendicular to the tangent planes, or to the surface, in fact. And then you have this other function. This other function has a, it's like, you can think of this being a function of 3 variables. So it also has a gradient. And remember, the gradient is like a vector. But this vector is completely like unrelated to this other gradient, right? So in general, you have like another vector which looks like this, which is the gradient of this volume function. But it could be the case, right? So like what I'm trying to denote here is that the gradient of V is completely unrelated to the gradient of G, right? But maybe you are lucky and it just so happens that the gradient of V is parallel to the gradient of G at some point, right? So maybe there's like a place where the two gradients are parallel. And why would that be useful? Because imagine that you are at this location where the gradients are parallel and you move in the direction V, which is along the surface. So what would be the directional derivative of the volume? Let's call this vector direction vector U. Let me call this vector U. In general, what was the formula for the directional derivative?
The gradient of V, the dot product is the gradient of V with U.
Yes. Right. But if the gradient of V is at a place where the gradient of V is parallel to the gradient of G, right? That means that it is just like a multiple. So what does it, let me say it this way. What does it mean for two vectors to be parallel? That means that one is a multiple of the other, right? Because one is just like a rescaled version. So that means that the gradient of V should be some multiple of the gradient of G, and that multiple is usually written lambda. Okay, so this is just like a rescaling factor. So this is just a number. Okay. And so if you take the directional derivative of V in like the direction of a vector U, then that's again, like as was just mentioned, the dot product between the gradient of V with the vector U. But now if the gradient of V is parallel to the gradient of G, right? This would be the dot product between the gradient of G and U. But what would be the dot product between the gradient of G and U if you choose a vector U, which is like along the surface?
0.
It's 0 because the gradient of G is perpendicular to every vector along the surface. So this gives you 0. So that means that the directional derivative of v would not change along that point. And so that's like a critical point for v because the directional derivative is fixed. So oh, u is just a vector. Sorry, I should just said like u is a vector that gives like, u is a vector which is tangent to the surface. It's a unit vector, yes. Oh no, the unit the unit vector like let me do a different picture. Like so for example, if you had like the sphere, right? Where now x squared plus y squared plus z squared equals 1. This is like g. So here's like, this is the gradient of g on the sphere, and like u would be like any vector that's like along the sphere, like it's any vector like this, like any vector that you can use to move along the sphere. So it's like a vector that would give you like a longitude or like a latitude, basically.
I'm still confused on is u being calculated from the equation of the sphere?
No, you can think of it like u would be like the velocity vector of a particle that moves on the surface, if you want. U is like the velocity vector of a path or of a path on the surface. So like if you're driving on imagine that you're driving on the surface, on the sphere, on a car. That car has a velocity vector, right? That's what I'm calling u. Is that making sense? So like, like let me say it this way. Like if you had like, okay, yeah, let me draw the sphere again. Like imagine you're traveling from the imagine that you're traveling to the North Pole along this green line, right? Along this arc. So that has like that tangent vectors, right? Which are these brown ones. Do you see them?
Yes.
Those are the vectors that I'm calling u.
Did you explicitly define that in our problem that we're currently working on yet?
No, I'm just saying that if you had happened like I'm just saying like if you happen to find a place, right? If you happen to find a place where the two gradients are parallel, right? At this point, the directional derivative will vanish regardless of the path that you chose that goes through that point on the surface. That's what I'm trying to say. So imagine you're driving. So I'm saying like if the gradients are parallel at some point on the surface, then the directional derivative of v vanishes along. Then the directional derivative of v vanishes for all the paths on this surface. Is that making sense? Or what was your question? So it's like, like the thing is like through a point on the surface, there are many paths that will go through it. Like, for example, you could move like through the green path, but you could also move through this red path, right? So there are many paths that you can draw on the surface that go through a particular point. So I'm just saying that no matter which path you had chosen, the directional derivative will be zero along any of those paths. Is that okay?
I think I'll understand more when you finish, if we finish out the example.
Yeah, so now like what I'm saying is that let's see. Do I have like a cube surface here? This is not going to work. Like what I'm saying is that you have here, like, imagine that you have, let me make it like this so that it looks like less like planar, so that you don't think it's really on a plane. Imagine like you see this red dot. So I'm saying, imagine that at this dot, at this point, all the both vectors are parallel, right? Then I'm saying that you can choose, like what that means is that you can choose like a path that goes through this point on the surface, like this purple one, right? And the directional derivative will be zero along the direction given by this path, basically. Because the gradients are parallel, so, and you knew that the gradient was already perpendicular to one of the vectors. But right, at the end of the day, like this all boils down to, like, the whole point of like the Lagrange multiplier method is to determine when the two vectors are parallel. So like the whole, like what I'm trying to say is like, maybe just to summarize this strategy, is that in this method too, you just determine when the two gradients are parallel. So one function was this one. The other function is like one that I called the level surface function. Okay, well, I promise that this method is faster. So let's see if this is true. What's the gradient of V? Is that making sense? That's the gradient of V, right? So far, so good. What's the gradient of G? That's the gradient of G, right? And so you need the two vectors to be parallel. So when is the gradient of V parallel to the gradient of G? Well, that's when one is a multiple of the other. This lambda is what people call the Lagrange multiplier, just by the way. This is like a constant number. So this gives you an equation that yz, xz, xy equals lambda times y plus 2z, x plus 2z, 2x plus 2y. Okay, and that translates into, remember, like two vectors are equal if their entries are the same. So this means that yz equals lambda times y plus 2z, and then xz equals lambda times x plus 2z, and then xy equals lambda times 2x plus 2y. Is that making sense? So far, so good. Are there any questions about this? So this is what you get by set, like what I'm saying is that this is what you get by asking the two gradients to be parallel to one another. How would you solve this system of equations? What could you do, for example?
Could you multiply each side of each equation by the variable that it's missing?
That's a good idea. Let's see if that, how much easier does that make your life? Yes, that's one way to do it. Another thing I think for this part is almost equivalent to it is that, like, for example, you could subtract 2 with 1, right? If you do 2 minus 1, you get xz minus yz on the left-hand side, right? And the right-hand side becomes lambda x plus 2 lambda z minus lambda y minus 2 lambda z, right? Is that making sense? So that's what you get if you do if you subtract the left-hand sides of 2 and 1, and you subtract the right-hand sides of 2 and 1, right? So what does the first, like, what does the left-hand side here becomes? It becomes z times x minus y, right? And here, what do you have? These two terms go away, right? So you get lambda times x minus y. Is that okay? So far, so good. Are there any questions about this? Are there, so is this okay with everyone? Or wait. There's another chance, right? What can you do here? You can factorize x minus y. Right? Is that making sense? And so what's the other option, right? Is that x equals y. So already immediately you get that x equals y, right? As a possibility. Is that making sense? So far, so good? Now, if x equals y, that actually brings you back to what we found a long time ago, right? I mean, this is like, once we know that x equals y, we can find the same values that we found before, right? With this, look at what we did before, and then with like, you get to the same conclusion. Okay. So the only null thing that you have to think about is whether or not you get something interesting from the chat option that lambda equals z. Okay. Which was that x was like root of 10 over root of 3, and y was root of 10 over root of 3. So let's see what happens if lambda equals z. Or z, yeah, lambda, let's do it like that. Well, what happens with the system of equations? It becomes like yz equals lambda, but now lambda is z. So lambda would be, sorry, that I have to go. It would be yz plus 2. Oh, this is so great. Like, let's, this is so good. Let's see, like, what if this is going to work? Yeah. What happens if lambda equals z? Let's go back to the first equation. Which was yz equals lambda y plus 2z. If lambda equals z, then this becomes yz equals zy plus 2z squared. Is that okay? Because I'm putting here lambda equals z. So far, so good. And so what can you conclude in this case? Yeah, because then you get that 2z squared equals 0. So z equals 0, and then the volume is 0, and that's not interesting, right? Done. And then you're done. And this is a solution of the problem. So do you see the difference between the two methods? So let me summarize what Lagrange multipliers says. So you have a function f. This is usually the name that is given to this function. You have a function f of 3 variables, which is the one that you want to minimize or maximize. So this is like the volume in our problem. So this is the one that you want to find. You want to maximize or minimize this one. So this is like the volume in the previous problem. And then you have a function g, which is like the constraint function, like the one that's defining like the level surface. So this is the constraint equation, or like the one that's defining the level surface. And the Lagrange method says that the critical points of f, or if you want to, the points that give you the max or mean are those for which the gradients are parallel. So if you want to find the max or mean of f, you must solve this system. Okay, and here lambda is a constant called the Lagrange. Was someone going to ask something?
Yeah, I was going to ask if you could just briefly summarize like the situational difference between this and everything we were doing up until 14.7 that like we couldn't use this.
The difference is that the problem right is that in this context, right, x, y, and z are not independent variables, right? Because sorry, just to go up for a second, like in this problem, right, like at the very beginning of this problem, I told you that this surface area had to be 10, right? That means that x, y, and z are not like, in the context of this problem, if you change one, you are affecting the other variables, right? So finding the max or mean of the function is no longer as simple as just finding where the partial derivatives are 0. If you're taking just like the partial derivatives with respect to all of the 3 variables, because like the 3 variables are not independent of one another. Is that making sense? So the difference, sorry, where should I go scroll up before I back to the work of finding the gradient? Like here, you mean? Like what I'm like the difference is like in the previous problems, like in section 14.7, is that it gave you like a function of 2 variables, right? But x and y are thought of as variables that you can vary on your own, right? Here in this context, if I give you like the formula for the volume, right, which is a function of 3 variables, the problem is that x, y, and z are not variables that are unrelated because they have to satisfy the constraint equation. Is that making sense? So that's why they cannot, you cannot just like find the partial derivatives with respect to x, y, and z. That they give you nothing. I mean, you cannot just set the partial derivatives with respect to x, y, and z to be 0, because like the partial derivative with respect to z in a way is like a combination of the partial derivatives with respect to x and y, because z is like a function of x and y. Is that making sense?
Is this going to be covered on the exam today or no?
No, this is here.
Any optimizations as well?
Well, if by optimization you mean, I mean, if it's just like a function of 2 variables, and you just find the max, the max and mean, that's okay. That's the previous, like this is for the, like that's for the exam, but not like in the Word version that like, oh, you start with this volume and you want to make it as large or big as possible. That's for the next exam. Is that making sense? So I mean, like by optimization, if you just mean like if you're given like a function of 2 variables and you find the max and mean, yeah, that's on the exam, but not where you have to find the function that you are trying to find the max and mean of. That's what I mean, I suppose. Yeah, you cannot use. I guess by MATLAB. No, yeah, you cannot use MATLAB. Oh. I just meant like, no, I just meant that if z equals 0, then the volume, like that's actually means that this is bad. So you can ignore this case. Let me do another example because I think this could be actually more illustrative. Could just convey the point. Like, let's say that you want like, let's say that you have this plane, right? 2x plus y plus 3z. Okay, and you want a point on this plane. You want to find the point on the plane that's closest to the origin, right? So what does that mean? You're trying to find like the distance between a point on the plane and the origin, right? Like there's this distance, right? And you're trying to make that as small as possible. So what's the formula for the distance between any point and the origin?
Square root of x squared plus y squared plus z squared.
Yes. Now, in fact, if you look at the, I mean, there was actually like the previous conceptual problem of last week asked you like, how are the critical points of a function and its squared related? And I don't know if you remember the discussion of the conceptual assignment, but essentially the idea is that they're essentially the same critical points. So this is why if you ever did like Calc 1 optimization problems that involve square roots, they usually would forget about the square root. And so you could just work with the function which was like x, y, and z without square roots, like x squared plus y squared plus z squared. Is that okay? So you don't need to keep track of the square roots. Yeah, you should check the boundary lines for those absolute max min problems, like in the triangle, yes. Because sometimes the max, like there you can find something that lies on one of the edges. So what I'm saying is that instead of like, well, all my, like the point here is like, instead of working with the square root, like you can forget about the square root because the max and the mean are the same. Like if you find a point that gives you like a max for the square root or a mean for the square root, the same point will give you the max or the mean for the thing without the square root. So so that's like the function that we're working with. But again, this is like, it looks like a function of, I mean, it is a function of 3 variables, but the whole point is that the variables x, y, and z are not independent of one another. Is that making sense? Because like you're not like choosing a point randomly in space. You're choosing a point in such a way that it belongs to this plane, right? Is that okay? So you're like, there's like a constraint because x, y, and z are not free to be whatever they want. The constraint is that 2x plus y plus 3z equals 5. So there's this constraint function, which is the 2x plus y plus 3z equals 5. Okay, is that making sense? And so like again, like if you were just trying to make f, if you're trying to make f as big or small as possible, you just have to take into account the fact that x, y, and z are not like independent variables. And like one way to take that into account is by solving for z, for example, right? So that you make f a function of 2 variables, but that's not what we're doing right now. Like the alternative method is to use the Lagrange multiplier where you just ask for the gradients to be parallel. So in the Lagrange multiplier method, you just like ask for the gradients to be parallel.
So will we sometimes be given the constraint equation and sometimes be given the, I forget what the other one is.
Well, that's like the other one is like the optimizing function, like the function that you want to optimize. Like you are usually given the, I mean, you will always be given the constraint equation in some way or the other. If it's like a Lagrange multiplier problem, yeah. Is that what you were asking me?
Well, I guess in this case, we kind of had to find the optimizing.
Yeah, you sort of had to find the optimizing function because it was given like in words, if that's what you mean. Right.
Okay, right.
Yeah. But I mean, if it's given in words, like it should be a straightforward thing to find. It should not be something that's a complicated function to find. Right. That's, yeah.
Okay.
So what's the gradient of f? That's 2x, 2y, 2z, right? What's the gradient of g? That's 2, 1, 3, right? So that means that 2x equals lambda. That means that 2y equals, sorry, 2x equals 2 lambda. That means that 2y equals lambda and 2z equals 3 lambda. Is that okay with everyone? Oh, g is just the name that you give to the constraint. The constraint was given to you because they told you that 2x plus y plus 3z equals 5. So like g is always the name for the left-hand side of the constraint. So g is just the name that you give to the equation that you're setting equal to a constant. And so what do you do here? Like the easiest thing to do in this case is like write everything in terms of lambda. So you can say that x equals lambda, then y equals lambda over 2, and z equals 3 lambda over 2. Is that making sense? Are there so far so good? So now everything is in terms of lambda, but you can also use the fact that 2x plus y plus 3z equals 5. So now you secretly have another equation because you still can use. And so if you do that, you get 2x becomes 2 lambda plus y becomes lambda over 2 plus 3z becomes 9 lambda over 2 that equals 5. And if you solve for this, like you'll find that lambda equals 5/7. Okay. And so once you know the value for lambda, you know that the point you can plot go back to find the values of x, y, and z. So you get x equals lambda, so x equals 5/7. Y gives you lambda over 2, so that gives you 5/14, and z becomes 15/7. Sorry, 15/14. So the point is 5/7, 5/14, 15/14. Okay. Is that making sense? So that's like what the Lagrange method says.
I have a question.
Mhm.
So, never mind.
Sorry, just to answer the question of the chat. This did minimize, but we never checked this. So in this context, you never apply like a version of the second derivative test. So like I should add that as a remark. Here you don't have to check the point that you find minimizes or maximizes. So yeah, sorry, you can like think someone was going to ask me something. So oh well, so I'm not sure what you mean by equations backwards.
Professor,
Yes.
I'm not sure if this is what Austin meant, but I was thinking like, can't lambda also be 7/5 in the last example? Like if you put lambda on the other side of the equation?
Oh, like
That might be what Austin meant.
why is lambda on the like next to G, you mean?
Yeah, exactly.
Like, well, it's just like a historical convention because, right, if you have written it like on the left on, if you had written like lambda times gradient of f equals gradient of G, then like lambda would be flipped, right? Yes. But that's okay. Okay, no, I see. Right. How, like, I guess the question was, how do you differentiate between the the function that you are optimizing versus like how do you know which one you call f and which one you call g, right? The one that gets called g is the one that's being set equal to a number in the problem. So like here, this one was being set equal to a particular value, so that's the g. So g is always the one that's set equal to a constant, and f is like the other equation. Is that making sense now? So G is always the name that goes for the one. Right. And then we had this question about x squared plus y squared plus z squared. Like, that's just because, like, sorry, there was like, I mean, the actual, like, the easiest explanation is that if you go to one of the conceptual assignments, like, let me show it to you. Here it is. If you have a critical point of a function, then that's also a critical point of the square of the function. And like basically the converse is also more or less true. So when you're finding critical points or like things that maximize or minimize, it doesn't matter if you're working with that function or its square. It's just that it's easier to get rid of the square root for computing the gradient. Is that making sense? Any other questions about this? Yeah, just to make the algebra easier when you compute the gradients. Did I forget any other questions or? We'll probably do another example next time on a Lagrange multiplier so that the method gets like absorbed. But you'll like there are other like more solved problems on the PDFs. But like you shouldn't like overthink too much about how the method ends up I mean, how we arrive to the method, but rather like how you just use it in practice. It's just like it was just to give you like an idea of where it comes from, but I guess it was a little bit too, the execution was a little bit difficult to do correctly. But okay, I'll see you at 3 if you need to show up for office hours. Otherwise, good luck on the exam. Oh, right. If you don't want to use Lagrange multiply, let me write it here. If you don't want, right, that's a good question. So if you don't want to use Lagrange multipliers, I'll write this here. If you don't want to use Lagrange, you have to solve for z, right? So you can say like z equals 5 minus 2x. Is that making sense? Like, because you use the equation of the plane to solve for z, right? Is that okay? And then like the function f becomes a function of 2 variables. And then you just look for, like, you think of this as a function of two variables, and then you just look for where the two partial derivatives are 0. Yeah. Is that okay? Anyone else? Good. So yeah, I'll see all of you. Well, or whoever wants to show up at 3. If not, just shoot me an email if there are like any questions that arise. So, you too. Bye. When you mean video, I said that if you watch the written assignment video before the exam, since that was about gradients, that could be useful. I mean, because it's about gradients. So if you go to the conceptual problems website, the Canvas website where I post the conceptual problems, there's like a written assignment, and there was a 20-minute video that I referenced. So you can watch that one if you want. Well, in this context, because it's an applied problem, you would not check with the second partial derivatives that it gives a minimum, but it will. It's just that we are avoiding doing that in these problems. Yeah. Good. Perfect. Excellent. So yeah, good.